2.5-inch SATA SSDs and the SATA interface. When you look at a 2.5-inch solid-state drive, also called an SSD, you're looking at the form factor that brought flash storage into the mainstream. These drives are rectangular, flat, and about the size of a slim smartphone. They plug into the same SATA ports that old mechanical hard drives used, which made the transition incredibly easy for anyone upgrading an older system. If your computer had a hard drive, it could handle a SATA SSD. No special adapters, no BIOS updates, no headaches. The SATA interface, which stands for Serial Advanced Technology Attachment, is the physical connection and communication standard these drives use. It consists of two cables. One is the SATA data cable, a thin red or black cable that connects the drive to your motherboard. The other is the SATA power cable, which comes from your power supply and delivers electricity to the drive. This dual cable setup adds a bit of bulk to your build, but it is straightforward and universal. Performance-wise, SATA SSDs were a massive leap over spinning hard drives. Boot times that used to take 2 or 3 minutes suddenly dropped to 15 or 20 seconds. Programs that crawled to life now opened instantly. Even ancient laptops felt usable again. But here's the catch. SATA SSDs max out at around 550 to 600 megabytes per second in both read and write speeds. That limitation is not because the flash memory inside is slow. It is because the SATA interface itself is the bottleneck. Think of it like this. You have a sports car engine, but you are driving on a narrow dirt road. The car can go fast, but the road will not let it. SATA 3, the most common version, physically cannot push data faster than about 600 megabytes per second. So even if manufacturers wanted to make a faster SATA SSD, they could not. The road has a speed limit. For budget builds or adding extra storage to an older machine, SATA SSDs still makes sense. They are cheap, reliable, and widely available. A 500 gigabyte drive might cost you $50 to $75, and a 1 terabyte drive sits around $80 to $100. Boot times in the range of 10 to 15 seconds are typical, which is still far better than a hard drive. But if you are building a new system or want the fastest possible performance, SATA is not the answer anymore. The M2 form factor and AHCI protocol. Now we need to address one of the biggest sources of confusion in the SSD world, the M2 form factor. A lot of people think M2 automatically means fast. Others assume M.2 and NVMe are the same thing. Both assumptions are wrong, and this misunderstanding costs people money and performance. M.2 is simply a physical shape and connector type. That is it. An M.2 SSD looks like a stick of gum or a thin circuit board with chips soldered onto it. It plugs directly into a slot on your motherboard without any cables. No SATA data cable, no power cable, just a single connector and a small screw to hold it in place. This makes M2 drives perfect for laptops where space is tight and for desktop builds where you want a clean, cable-free interior. The M2 designation comes from the second generation of mini SATA, hence the M in the name. These drives are standardized at 22 millimeters wide, but the length can vary. You will see M.2 drives labeled as 2242, 2260, 2280, or 22110. The first two digits are always 22, the width in millimeters. The last 2 or 3 digits represent the length, so an M.2 2280 drive is 22 millimeters wide and 80 millimeters long. Here's the tricky part. Not all M.2 drives are fast. Some M.2 drives are actually SATA drives squeezed into the M.2 shape. They use the same SATA protocol and are still limited to 550 to 600 megabytes per second. So you could buy an M.2 SSD thinking you are getting cutting-edge speed, plug it in, and discover it performs exactly like a 2.5-inch SATA drive. Same speed, different shape. If SATA is the physical connection, AHCI is the language that connection speaks. AHCI stands for Advanced Host Controller Interface, and it is the communication protocol that tells your computer how to talk to a SATA drive. AHCI was designed back in the mid-2000s, long before SSDs became common. It was originally built to handle mechanical hard drives with spinning platters. The problem is that SSDs do not have moving parts. They use flash memory, which can handle thousands of simultaneous requests. But AHCI can only manage one command queue with up to 32 tasks at a time. Picture a busy supermarket with 50 checkout lanes, but only one cashier is allowed to work. That is AHCI, stable and compatible, but painfully outdated for modern storage technology. The NVMe protocol. NVMe stands for Non-Volatile Memory Express, and it is the modern protocol designed specifically for SSDs. Unlike AHCI, which was a carryover from the hard drive era, NVMe was built from the ground ground up to take full advantage of flash storage. This is not just an incremental improvement. It is a complete rethinking of how storage should work. The first major difference is parallelism. Where AHCI supports one command queue with 32 tasks, NVMe supports up to 64,000 queues with 64,000 commands each. That is over 4 billion potential requests happening simultaneously. Your computer will never actually use all of those queues, but the point is that NVMe removes the bottleneck entirely. If AHCI was the single supermarket cashier, NVMe is like opening 1,000 registers at once. Suddenly, the lines disappear. Latency is also dramatically lower. Tasks that took 30 microseconds under AHCI can drop to just 10 microseconds with NVMe. That might not sound like much, but when your computer is making millions of tiny requests per second, those microseconds add up. The result is a system that feels instantaneous. Games load faster. Large files transfer in seconds. Multitasking becomes seamless because the storage is no longer the slowest part of your system. NVMe drives also communicate directly with the CPU through the PCIe bus. This direct connection eliminates several layers of overhead that SATA and AHCI introduce. The data path is shorter, cleaner, and faster. It is like going from a winding dirt road with speed bumps to a straight highway with no traffic. Real-world performance differences are significant. A SATA SSD might boot your operating system in 15 seconds. An NVMe drive can do it in 5 seconds or less. Loading a game from a SATA SSD might take 30 seconds. An NVMe drive can cut that to 10 seconds. Large file transfers that take minutes on SATA can happen in seconds on NVMe. The word non-volatile in NVMe means the memory does not require power to retain information. You can shut down your computer, unplug it, leave it off for a year, and your data will still be there when you power it back on. This is different from volatile memory like system RAM, which loses everything the moment power is cut. NVMe is now the standard protocol for modern high-speed SSDs. PCIe lanes and generations. PCIe, which stands for Peripheral Component Interconnect Express, is the highway that NVMe drives use to communicate with your CPU. If NVMe is the protocol that manages traffic, PCIe is the actual road that data travels on. Understanding PCIe is critical because it directly determines how fast your SSD can perform. PCIe connections are divided into lanes. Each lane is a dedicated pathway for data to travel. You will see PCIe devices labeled as X1, X4, X8, or X16, where the number represents how many lanes the device uses. Most modern NVMe SSDs use X4, meaning they occupy 4 PCIe lanes. Graphics cards typically use X16. More lanes mean more bandwidth, which translates to faster data transfer. But lanes are only part of the equation. PCIe also comes in generations, and each generation doubles the bandwidth of the previous one. PCIe 3.0, which has been the standard for years, offers about 1 GB per second of bandwidth per lane. So a PCIe 3.0 X4 SSD has roughly 4 GB per second of total bandwidth, which translates to around 3,500 megabytes per second in real-world performance after accounting for overhead. PCIe 4.0 doubles that bandwidth. Each lane now provides about 2 GB per second, so a PCIe 4.0 X4 SSD can reach around 7,000 to 7,500 megabytes per second. PCIe 5.0 doubles it again, pushing bandwidth to about 4 GB per second per lane. A PCIe 5.0 X4 SSD can theoretically hit 14,000 to 16,000 megabytes per second. Compare that to SATA's 550 megabytes per second, and you are looking at speeds that are 25 times faster. Your motherboard and CPU need to support the generation you want to use. If you buy a PCIe 5.0 SSD, but your motherboard only supports PCIe 3.0, the drive will work, but it will be limited to PCIe 3.0 speeds. The drive will downclock itself to match the slowest component in the chain. PCIe lanes are also a finite resource. Your CPU and motherboard only have so many lanes available, and they have to be shared across all your devices. Your graphics card might use 16 lanes. Your SSD uses 4 lanes. At some point, you run out of lanes, and devices have to start sharing bandwidth. 2 lane vs 4 lane NVMe drives. Within the NVMe world, there is another layer of complexity that trips people up: the number of PCIe lanes an individual drive uses. Most modern NVMe SSDIs use 4 lanes, labeled as X4, but some older or budget-oriented drives only use 2 lanes, 2 labeled as X squared. This makes a massive difference in performance, and the product listings do not always make it obvious which one you are buying. A 2-lane NVMe SSD has half the bandwidth of a 4-lane drive. If you are using PCIe 3.0, a 2-lane drive caps out at around 2,000 megabytes per second instead of 3,000. 7500. With PCIe 4.0, a 2-lane drive maxes out around 4000 megabytes per second instead of 7500. You are still getting better performance than SATA, but you are leaving a lot of speed on the table. The problem is that some manufacturers do not clearly advertise whether their drive is 2-lane or 4-lane. They might just slap NVMe on the box and hope you do not notice. The best way to identify which one you are getting is to look at the advertised transfer speeds. If a drive claims 3500 megabytes per second or higher on PCIe 3.0, it is almost certainly a 4-lane drive. If the speeds are closer to 2000 megabytes per second, it is probably a 2-lane drive. Physically, there used to be a way to tell the difference by looking at the keying on the M.2 connector. 4-lane NVMe drives typically have a single notch, called M keying. 2-lane NVMe drives sometimes have 2 notches, called B and M keying, which makes them look identical to SATA M2 drives. But this is not a reliable method anymore, because some 2-lane NVMe drives now use single-notch connectors as well. The pricing difference between 2-lane and 4-lane drives is usually not huge, maybe $10 to $20 for the same capacity, but the performance gap is significant. If you are spending money on an NVMe drive, you want the full 4 lanes. There is no good reason to buy a 2-lane NVMe drive unless it is heavily discounted. Most modern motherboards provide full X4 connectivity to their M.2 slots, but some budget boards might only wire up 2 lanes to certain slots. Check your motherboard manual to confirm. You could buy the fastest drive on the market and still get mediocre performance if your motherboard cannot support it. Putting it all together, what to buy? Now that we have broken down every component, let's put this all together so you actually know what to buy. The confusion around SSDs comes from the fact that multiple terms describe different aspects of the same drive: SATA, M.2, NVMe, PCIe, AHCI. These are not competing technologies. They are layers that stack on top of each other. SATA is both a physical connector and a communication protocol. When you buy a SATA SSD, whether it is the 2.5-inch form factor or M.2 form factor, it uses the AHCI protocol and maxes out at around 550 to 600 megabytes per second. The shape does not matter. A SATA M.2 drive is not faster than a 2.5-inch SATA drive. They are the same speed, just different shapes. M.2 is purely a form factor. It tells you the drive is small, slim, and plugs directly into your motherboard. But M.2 alone does not tell you anything about speed. An M.2 drive can be SATA, which is slow, or NVMe, which is fast. You have to check the specifications to know which one you are getting. NVMe is the modern protocol that makes SSDs fast. It bypasses the limitations of AHCI and allows the drive to communicate directly with the CPU through the PCIe bus. PCIe is the highway that NVMe uses. The generation, PCIe 3.0, 4.0, or 5.0, determines the maximum bandwidth. The number of lanes, X2 or X4, determines how much of that bandwidth your drive can actually use. So, when you are shopping for an SSD, here is what you need to look for. If you are on a tight budget or upgrading an older system, a 2.5-inch SATA SSD is fine. It will still feel dramatically faster than a hard drive. You will spend around $50 to $100 for decent capacity. If you are building a new system or want the best performance, go with an M.2 NVMe drive using PCIe 4.0 with X4 lanes. This will give you speeds around 7,000 megabytes per second. Boot times drop to under 5 seconds. Games load almost instantly. Prices have come down significantly, so you can find quality PCIe 4.0 NVMe drives for around $100 to $150 for 1 terabyte. For most people building or upgrading a PC in 2026 and beyond, the answer is simple. Get an M.2 NVMe drive with PCIe 4.0 and X4 lanes. Fast, efficient, and built for the future. Check the next video for more tech breakdowns that actually make sense.